Okay, let's get started. Okay, quiet, please. Okay, so we've got a bit of admin stuff to get through before the lecture. So firstly, the practice June test coming up. So the scope for that will be all of the stuff we did in term 1 and the stuff we did now in term 2 up to this part. Okay, so that will be for the practice. I'll get to you now. So that will be for the practice. And then remember for the real June test, that will include the last bit on curve sketching as well. Okay, did that answer your question? Okay, so for the practice one, only up to the stuff we're doing today with the approximations. And then the real June test later on, that will be everything term 1 and term 2. Okay, all of that stuff together. Now, the practice June test will be counting for marks. If I don't make it for marks, then half of you don't show up, and then what's the point of having a practice test? Now, you get to decide the weighting. You have two options. Option number 1, we use the practice June test to fill in the missing quiz marks. Okay, so when we go through especially term 3, there's a couple days that we miss because of holidays and exams and all of that. So we won't get exactly 20 quizzes for the year. So we can use this practice test mark to make up for the missing ones. Remember, the quizzes count altogether 12.5% for the year. So we can use it to maybe boost your quiz marks. Or we can use it as a class test 5 kind of mark. And that will boost your class test 1 mark. Okay, so a lot of you did all right in the class test 1. A lot of you did very bad in class test 1. It can average out to make your class test 1 a little bit better. Now, we can treat this like a democracy, so you can vote. So you either vote to use the practice quiz to replace your quiz marks, so it will count less and boost your marks less. But if you do badly, it's a bit less. Or we use it as a class test 5 kind of thing to average with your class test 1. That if you do well in that, it will boost your class test 1 quite a lot, because it'll be like 50-50. Or if you don't study for the practice test, it goes down. I suggest you study for the practice test either way, because the June test is back from moderation. The external moderator didn't change it too much. It's about the same, maybe a little bit more difficult, but it's about the same. So it will be a good help to see, right? If you treat it properly like a class test. So I'll leave it for you to vote. Hands up if you wanted to replace the missing quiz marks. 1, 2, 3, 4, 5. Okay, class rep, please take notes of that. There were 5 votes for the replacing the quiz marks. Just for the sake of completing this, hands up if you want it as a class test 5 to boost your class test 1. Okay, class reps, please have a look around. That's pretty much everyone else. Okay, class reps, please make a note of that. So your class weighting for the year will change slightly now. So if you look on your Student Central, you'll see quiz and class tests. For the class test, it will now be class test 1 and the June test together. So it will be class test 1, June test. Class test 2 will then be separate as class test 2. And then next semester will be class test 3, class test 4 as normal. So that won't change. Everyone okay with that? All good. Yeah. Next week, Tuesday. Yeah. So we treat it exactly the same like a test. It's weighted a little bit lower because we haven't finished everything for this term. So the usual hour-and-a-half normal test type thing. Okay. So again, the scope will be the stuff from the term 1, class test 1, up to this bit here for term 2. Okay. And then once you've done your studying for that, to study for the class test 2, you've already done most of it because you've studied for this. And then for the June test, again, you've already covered everything already. The types of questions for the practice test and the real test are exactly the same. So for the practice June test, if question 1 was a set theory proof, June test, set theory proof. If question 2 was on continuity, question 2 is continuity. I just changed it a little bit, right? I didn't remake the test. Yeah.
So the practice test would be like class test 1 2.
Practice June, yes. Yeah.
1 game.
Yeah. So it will be majority class test 1 and this little bit here for the class test 2. Yeah. So the idea is if you do well in the practice test, you're going to do well in the class test and the June test. It's the same sort of scope. Yeah. It's just that the June test has one more question out of 10 on the curve sketching, which we're doing next week. That's the only difference. Yeah. So once you've studied for this, it's one more chapter, and then you sort it for the June test. Everyone good with that? Okay. So again, class rep, please just make a note of that for the if anyone has issues with the weighting at the end of the year. Any issues before we go on to the lecture? Okay. Okay. So I'll make the adjustments on Student Central. You'll see the new weightings there. Okay. So today we've got a new chapter, approximation and errors. So in this lecture, we're going to go through linear and quadratic approximations. And then tomorrow, we're going to go through the estimating errors part. Very, very easy chapter, very easy marks for the test. There are some extra tutorial problems on this, quite a few problems. But if you understand the lecture material, that should be fine. Okay. But if you do need help, there are extra tutorial problems. Okay, so what's the idea between linear and quadratic? Why do we use these? So let's say we have some complicated function f. Okay, so complicated just depends on the problem that you're given. But we have a complicated function f. We would like to approximate this function. So we replace it with some easier function to work with near a certain point of interest. So we would like to approximate this function near some point of interest. For example, we can have some complicated function, and maybe we're only interested in the values near x equals 0. Like x equals 10, we're not interested in that, so near x equals 0. Instead of working with the complicated function, we're going to work with a simpler function, but in that case, it's only an approximation now, right? There's going to be some error involved in that. Okay, so the idea is to have our f of x being approximated by a polynomial. So we're going to write this as a0 plus a1x plus a2x squared plus dot 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 up to some an x to the n. Yeah, and we use the squiggly equals to show that this is not an equality between the two. It's only an approximation. Now, this is only one type of approximation. There's many approximation methods, but we'll be focusing on these two, linear and quadratic. Okay, so if you're looking in the textbook or online, there's other ones like the per day approximation. Don't worry about those ones. That's a bit too complicated. Only these simple ones for now. Okay, so how do we do this? Well, we've got our function f, and we've got this polynomial on the right-hand side. We don't know what those coefficients are. We're going to try to figure that out. The way we do that is we're going to match the function value on the left side and the right side. We're going to match the first derivative on the left side and the right side, and the second derivative. Okay, so if we match the function value, the first derivative, and the second derivative, hopefully it's a good approximation. Okay, so we want to match, number 1, the function value. Number 2, the first derivative. derivative. And number 3, the second derivative. If we continue this and match the third derivative and fourth derivative, then the approximation just gets better and better as we add on. But here we are going to stop at number 2 for the linear approximation. And then if we wanted a bit more accurate, we'll then stop at number 3 with the second derivative. I won't be asking you any questions after that. So it's only the first and the second. Okay, so let's go through that. So we're going to match up the function value, the first derivative, and the second derivative. At x equals 0, we're going to treat that as our point of interest. Remember here, we're interested in some point. Then later on, we're going to shift it to any other point. Okay, so just to make things easier, we'll do it at x equals 0, and then shift our answers afterwards. So we will evaluate these at x equals 0, just to make things simpler for ourselves. And then if we want this at any other point, we just shift our answer over. Then we can shift to any other point. Let's say x equals c afterwards. Okay. So let's go ahead and do this. So firstly, we want to match the function value at 0. So on the left-hand side, we're going to substitute 0. So we have f at 0. Okay. On the right side, we're going to substitute 0 because we want it to match. Notice all of the terms after A0, they go away. So A1 goes away, A2 all the way to AN, all of those go. We're left with A0. Okay, well that's great. We know what A0 is now. So in our polynomial approximation, A0 is just the function value at 0. Now let's match the first derivatives on both sides. So on the left side, the first derivative is just f prime, very simple. And then on the right side, we need the derivatives of all of those terms. So the derivative of A0, that's a constant, that goes away. Derivative of A1x, just A1. So we have a 0 plus A1 plus 2A2x plus dot dot dots plus n an x to the n minus 1. Okay, so that's what we get with the first derivative. Now we want this to match at x equals 0. So let's substitute. On the left side, we have f prime at 0. And on the right side, we see that everything after a1 goes away. So the a2 term all the way up to an, if we substitute x equals 0, all of that goes away. And we're left with a1. That's great. We have the second coefficient now. We have a1. Next, we're going to go for a2. Now we're going to look at the second derivative on both sides, and again, evaluates at 0. So let's do that. So we have the second derivative. Now on the right, a1 now goes away because it's the second derivative, and we have 2a2 plus dot dot dots. Then we have n minus 1, an x to the n minus 2. So we just do the derivative again for each of those terms. Again, we want this at 0, so let's substitute 0 into both sides. On the left side, we substitute 0. We just get f double prime at 0. And on the right side, everything after a2 has an x with it, so all of that goes to 0. That's great. We have a2 now. So a2 will be 1/2 f double prime at 0. Okay, so a2, that gives us up to x squared. If we wanted a cubic approximation, we would do the process one more time. Or if you want a fourth order approximation, you do it again, and so on. But here we're going to stop at quadratic. So from this, we get two approximations. So the linear approximation remember, this is still at x equals 0. We haven't shifted anything yet. The linear one will be the constant term and the x term. So we write it as L of x, L for linear, will be A0 plus A1x. We know what those are. So A0, that was f at 0. And A1, we know what that is. That's f prime at 0, x. Okay, that is the linear approximation at x equals 0. Now, if we wanted this at some other point, x equals c, we can just shift everything over to x equals c. So the linear approximation at x equals c. So instead of doing all that work again, we just shift our answer. So it will be L of x is now f prime not at 0 because we're interested in c. So it will be f prime at c. F at c plus f prime at c. And instead of x, we shift over to c. So it will be x minus c. Okay, so that will be the linear approximation at c. You can see if we put c as 0, we just get back to where we started. Okay, what about the quadratic approximation? Very easy. We just add on the x squared term. Okay, so again, we do it at x equals 0. If we're interested in any other points, we just shift over. So for the quadratic, we just call it q for quadratic. So this will be f at 0 plus f prime at 0 times x. And now we include the quadratic term. So that will be 1/2 f double prime at 0 x squared. Yeah, very easy stuff. Now, if we want this at some other point c, we just shift everything over. So this will be the quadratic approximation at x equals c. Right, we just shift everything. So it will be q of x is equal to the function value at c. Again, we're interested in the point c. Plus f prime at c, x minus c because of the shifting, plus 1/2 f double prime at c, x minus c squared, again because of the shifting. Okay, so we've got the linear approximation and the quadratic approximation. Please put boxes around these two. Those formulas will not be given to you. Okay. Any questions on how we get these formulas? All good. Okay, let's have a look at some examples. So number 1, given f of x equals 2 roots x, we've got 3 sub-problems here. So number 1, find the linear approximation at x equals 1. Number 2, find the quadratic approximation at x equals 1. And number 3, find the values of x for which the approximation L of x has an error less than 0.1. Okay, so like I said, this is only an approximation. There's going to be some error involved here. So at the points, x equals 1, there's no error because the function values match on both sides. But if you move slightly away from x equals 1, it's going to deviate, right, from the graph. So we want to find the x values where that deviation from the exact function is less than 0.1. Of course, with engineering, you have to have some approximation somewhere, but you don't want the approximation to be too large, otherwise bridges collapse. So 0.1, that's a pretty large error. Later on, when you guys are doing your bridge simulations and stuff, you'll put errors like 10 to the minus 5, something like that. Okay. But for our case, we're going to deal with larger errors like this. Okay, just to make things a bit easier. Okay, so let's go through these. So number 1, find the linear approximation at x equals 1. So we know what that's going to be like. So L of x will be f at 1, because we're interested in the point 1, plus f prime at 1, x minus 1. Right, we just have that from earlier. So what do we need? We need the function value at 1, and we need the derivative at 1. So let's see what those are. So f at 1, f is 2 root x, so we get 2 root 1, that will just be 2. Okay, what about the derivative? So f prime of x, that will be 1 over root x. Okay, so you just take the half down, minus from the exponent, so that will be 1. So here f prime at 1 is 1. Okay, so we have what we need there. Let's substitute into the equation above. So we have L of x is the function value at 1, so that will be 2, plus the gradient at 1, which is 1, x minus 1. So we get the following straight line. Now, for number 2, that's the quadratic approximation. So in that case, we need the second derivative. Okay, so f prime, let's write that as x to the minus a half. So we need f double prime. So take the minus a half down. So f double prime at 1, that will be minus a half. Okay, and we just substitute. So q, this will be f at 1. We already know that is 2. Plus f prime at 1, we know that is 1. Plus a half. F double prime at 1, we worked that out. That's minus a half. X minus 1 squared. Okay, easy stuff. You just do the derivatives, evaluate at the points, and then you substitute into that formula. All right. Any questions so far? Yeah. Number 2. So we're just using this formula here. So Q of x is f at c plus f prime at c x minus c plus 1/2 f double prime at c x minus c squared. That's the formula we derived earlier. So f, that will be 2 root x. And c, that was the point of interest, that's 1. So here we found f at 1, then f prime at 1, and then over here f double prime at 1. You just evaluate in the order. And then you just substitute. So this one, and this one, we substitute 2, 1, and minus a half. Yeah.
You have no how to derive this one.
No, you don't have to do, no.
Well, sure, right. Of course.
No, that was just getting the formula. No, you don't need to know that. Yeah. As long as you know this formula in pink here, and the one we have here in white, that's all you need to know. Only up to quadratic. Yeah. So after Anything x cubed, x to the 4, you don't need to know. Okay. Next year, you'll add more terms. But for now, it's just the linear and the quadratic. Okay. Any other questions? All good. Okay. Number 3. A little bit more difficult, but not too bad. So we want to find the values of x for which the approximation L has an error less than 0.1. In other words, the difference between the function value and the approximation, that's the error, right? We want that to be less than 0.1. So we want the function value minus the approximation. That gives us the error. It's the difference between the exact value and the approximate. This must be less than 0.1. So here, f, that is the exact value. This is the approximate value. Right, the difference between exact and approximate, that's the error. We want it to be less than 0.1. And the idea is find the x values. Okay, so we've got this inequality. We want to solve for x. Okay, so let's substitute the function. Let's substitute L and then solve the inequality for x. Okay, so the function, that was just 2 root x. The linear approximation, let's write that out. That's the L here. So 2 plus x minus 1. So just 1 plus x is less than, let's write this as 1 over 10. We're going to do some fraction stuff with that. Okay, so if we have the absolute value of something being less than 1 over 10, that means that it lies between minus 1 over 10 and plus 1 over 10. Right, that's just your absolute value rules. Yep. So from one inequality, we can drop the absolute values, and now we've got 2 inequalities. So one on the left there, one on the right. We want to solve for x, so let's try to simplify this a bit. We've got this minus 1 here, we can add to both sides. So on this left side, we can add 1, that will be 9 over 10. And then add on to the right-hand side, that will just be 11 over 10. Now, the issue is that root over there, that's giving us some problems. So let's try isolate the root x on one side. Then if we square both sides, that gets rid of the root. So that x in the middle there, let's add it on both sides so we can isolate that root term. Now that it's isolated by itself there, if we square both sides, that gets rid of the root. So I'm going to just write this as 2 inequalities. Then we can solve by squaring both sides. So on the one side, we're going to get 9 over 10 plus x squared. Again, we want to get rid of that root there, is less than 4x. And on the other side, again, squaring both sides, we're going to get 4x is less than 11 over 10 plus x squared. Once we do the squaring, then it's just a quadratic, right? Quadratic formula, easy enough to solve. Okay, so on the one side, we get 81 over 100 plus 2 times 9 over 10x plus x squared less than 4x. Okay, then on the other side, same sort of thing. 4x less than 11 over 10 squared plus 2, 11 over 10x plus x squared. Okay, so you know how this works. You take everything over to one side, solve for x, you got your inequality. Okay. Now I just want to show you what this looks like. Right, so just get your calculators, get those values there. We'll see if that's correct. Right, it's just quadratic formula, to find the value. So just check that. And then on Desmos here, I'll plot this and we can see if we get the right answer. Okay, so we have f of x is 2 square root x. So it's going to look something like that. And we're interested in the point at x equals 1. So we want to, zoom in on that point and work out the error. Okay, so let's put in our linear approximation L. So that was f at 1 plus f prime at 1, x minus 1. Okay, so that's the linear approximation. We reinvented the tangent line. Well, that's fine. Okay, so the linear approximation at that point is just the tangent line at that point. Okay, now if we zoom in very close here, you can see that this green line is very, very close to this red line. Okay, that's what we mean by good approximation. Okay, it's very close there. Now, if we go too far out, the error between the two starts getting quite large. What we want is that error between the two lines to be less than 0.1. Okay, has everyone got the values? Okay, please check. So we have the function value minus the linear approximation must be less than 0.1. And that gives us this little window here. So when you solve your quadratic, you should get these values here. Okay. It's around 0.5 and a bit after 1.5. Did you get that? Yes. Yes, no. I mean, you all know the quadratic formula. Please just find the values. What did you get?
0.46.
Yep, that looks about right. So it's a bit less than 0.5. Yeah. So that's the lower bound for the x values, and the upper one?
170.
Yeah, that looks about right, somewhere over there. Okay, so you can check that in Desmos. So for the homework problems and the tutorial problems, you just set it up like this, and then you can check if your bounds are correct. Okay, so let's just copy this picture over, and then you can check at home if you didn't do it here. Okay, so over here, solve for x. Okay, that should be somewhere there with these purple endpoints there. All right, any questions for this one? All good. Okay, so just solve for these x values. It should be somewhere here less than 0.5, a little bit more than 1.5. Okay, you can check that. Any questions before we move on? Okay, let's have a look at example 2. Okay, determine the quadratic approximation for f of x equals e to the minus x squared at x equals 0. Okay, so let's write out the formula, see what we need to find. So the quadratic one, that will be q. That will be f at 0 plus f prime at 0 times x plus 1/2 f double prime at 0 x squared. Right, that was the formula we got for the quadratic. So we have our function f. So we need f at 0, we need f prime at 0, and f double prime at 0. So let's go through the list. So f at x, that's e to the minus x squared. So f at 0, what will that be? 1. Okay, f prime. So the derivative of the exponential, that's just the exponential. And then the derivative of the exponent, that's minus 2x. So f prime at 0. Yeah, 0. We've got the x there, so it'll be 0. Okay, and then we need f double prime. Okay, here it's a little bit more complicated. Got the product rule. So let's do the derivative of the first one. So that's e to the minus x squared. We get another minus 2x, so that will be squared, plus e to the minus x squared and minus 2. Okay, f double prime at 0. Negative 2. Good. So we got f at 0, f prime at 0, f double prime at 0. We just substitute into the equation, we have our answer. So we have 1 for f at 0. F prime is 0, so we just leave out that linear part. And then the quadratic part, that will be 1/2 f double prime x squared. Okay. Let's have a look at this on Desmos like we had before. Okay, so we have f of x is e to the minus x squared. So it looks something like that. And we're interested in the quadratic approximation at 0. So q of x, that will be f at 0 plus f prime at 0. And we see it. We can't have a linear part. It's just a horizontal tangent line there. Okay, plus 1/2 f double prime at 0 x squared. Here we get that parabola that we had there. Again, notice very, very close to our points of interest. It's a very good approximation. The further out we go, right, it starts getting a bit bad. Yeah, over there. Yeah, so it should look something like this. Yeah, also, please work on your function sketching. All right. If I give you a function, I'll say draw the function and the linear and quadratic approximations. You should be able to sketch something like this. Yeah. So drawing the straight lines at a point, drawing the parabolas at a point, you should be able to do that. Right. Any questions with this one? Yeah. No, you're not given any y values. It's only at some x point. Yeah. So you got the function and you're interested in some x point. Yeah. The y value is just f at x, whatever x is given. Okay. Any other questions? All good. Okay. Number 3. Okay. Determine the values of x. For which the approximation of x of f of x equals 1 over x plus 1 has an error less than 0.5. Okay, so like before, we're going to set up the inequality, solve for the x values, and then we can check our answers. Okay, for all of these, you know how to use the Desmos now. You can check your answers to see if they're right. Okay, so we want the linear approximation, at x equals 1. Okay, so we need to work out the linear approximation, solve that inequality, and then get the lower bound for x and the upper bound for x. So L of x, that will be f at 1 plus f prime at 1, x minus 1. Okay, so we've got the formula. We need f and we need f prime. Okay, what's f at 1? 2. Good. And then f prime. What's that going to be? What's that? Minus 1 over x squared. Good. Okay, so f prime at 1, that will just be minus 1. Okay, so we got our values. If this was the quadratic, you'd have to find f double prime then. So that's the linear one. Let's substitute in. Okay, so f at 1, that's 2. F prime, that will be minus 1. X minus 1. Okay. So what do we get for this? For our straight line tangent? It's not that late in the day. Can't be that sleepy. What do we get? Yeah, 3 minus x. Okay, so we've got our linear approximation. Now we want to find the x values for which the error is less than a half. So let's set that up. So the error, that will be the difference between the function value and the approximation. We want this to be less than a half. Okay, so we substitute the function that's given. We substitute L, we just work that out. We can solve that inequality for x. So the function, that was 1 over x plus 1. Our straight line we got there, that was 3 minus x. Less than a half. Okay, let's simplify a little bit, and then we can solve for x. So this will be the absolute value. We can drop that if we say that this is between minus a half and plus a half. Okay, so we dropped the absolute value, but now we have two inequalities. Okay, then we can simplify a little bit. So plus 1 minus 3, we got minus 2 there. Okay, this 1 over x is going to cause us some issues. So let's simplify a little bit more and then we'll figure out what to do with that. So we've got a minus 2 in the middle. Let's add that on the left side and the right side. So minus a half plus 2 for the left side. What do we get? 1.5, yeah. Yeah, I'm getting worried about your fraction work. Okay, so 3 over 2, we're left with 1 over x plus x. Other side, if we add the 2, 5 over 2. Okay, my faith is restored a little bit. Okay, so we can split this up into two inequalities, or you can treat it as one. I'll leave that up to you. So let's split it into two. So we're going to have the one part for the left side, another part for the right side. Then we can solve for x. Okay, so we have 3 over 2 less than 1 over x plus x. We'll just treat that separately on the one side. And then on the other side, we have 1 over x plus x is less than 5 over 2. Okay, now I don't really like working with these fractions, so let's try to clear that. So the x we need to clear, the 2 at the bottom we want to clear. Let's multiply through by 2x. Okay, that'll clear the fractions there. Okay, so on the one side, we're going to get the 2's will cancel there, so we just have 3x. Other side, we're left with 2 and 2x squared. Okay, it's a bit easier than working with fractions, but if you want to keep the fractions, that's fine as well. So we have 0 is less than 2x squared minus 3x plus 2. Again, nice quadratic. We can solve for x there. On the other side, you can do the same thing. Okay, so we get 2 plus 2x squared is less than 5x. Take everything over to one side. Just use the quadratic formula again. Okay, what do we get for the x values? Just quadratic formula to get the x values there. Sorry? Okay, well, you throw that out. That doesn't help us. We need a lower bound and the upper bound. Yeah, you might get that, but you throw that out. So we're looking for the smallest x value and the largest x value for that window. 3 over 4. No. No. Smallest x value, largest x value from the solutions. Yeah? 0.5. Yeah, that's one of them. Good. And then the larger x value? 2. Perfect. So the x interval will be 0.5 less than x less than 2. Yeah, perfect. Let's have a look at that here. Let's get rid of that here. So we have f of x was 1 over x plus 1. And then we've got the linear approximation. That was f at 1 plus f prime at 1, x minus 1. Okay, again, so we zoom in on the point 1. We see the linear approximation there in green and our function in blue. So very close to the point, it's a pretty good approximation. Further out, it kind of doesn't work anymore. So we want absolute value of our function minus the approximation. That gives us the error. We want that to be less than a half. We zoom in a little bit. There we go. The start of the window there is 0.5 and the ending over there at 2. Okay, so yeah, that's right. Half to 2. Okay, so let's just copy this and then you can check at home. So this interval here, that's what we have in purple over here. Okay. Any questions for this one? Yeah.
So what did we do F1?
At 1. Because it's at x equals 1. The approximation's at x equals 1.
So how do we know when we use which creation factors that what's to get the interval?
The interval. That's just from solving this. From solving these.
So which one do you know then use? Because the second one gives you the answer.
This
That's
yeah, one of them you throw out because that doesn't work. So the idea is the following here. If we look over here, when you split this into 2 parts, right? You're going to have one section, for example, the function is above the approximation. On the other part is the function is below the approximation, right? Because of that absolute value. One will be above, one will be below. In certain situations, the function is always above the approximation. It's always above, so there's no 2 answers. Other times, the function is always below the approximation. And other times, we have something like this. So here, we see this function is always above. So the absolute value, it doesn't mean anything. Function minus the approximation is always positive. So that other part you throw out. But you don't always know what it looks like. So that's why we do it with the absolute value, because we don't know which is above which. In this case, f is always above L, so that other part of the absolute value is useless. We throw that out.
the absolute value of f minus f.
Yes. Yeah. If you know that the function is always above, we can drop the absolute value over here, and we get this part over here. We get the same bit there. But if we have L of x minus f of x, you see now that becomes negative over here. right? Because we swapped the order. So just to save us from figuring out which way around it goes, we put the absolute value. Yeah. So always put the absolute value and then just throw out the inequality that we don't need. Okay. But I mean, you've done inequalities before, right? In high school, you throw away one, no solution or whatever. Yeah, I assume you know how to solve these, right? Okay, if you don't know how to solve it, I mean, I can't help you with that. You have to figure that out. Was it paper 1, question 2, solve the inequality? I'm sure you've done plenty of those. Okay, if you're still confused, you can see me afterwards. I can help you out. Otherwise, look in the algebra notes. Okay, the algebra notes, there's the trig and the factoring and all of that. There's some problems with this. Okay. Last thing for today, some homework. Okay. Determine the linear and quadratic approximations. At x equals pi for f of x equals x sine x. Okay. So for questions like this, x sine x, I'm not going to expect you to sketch that. It's a little bit too difficult. But those other functions like we had before, 2 root x, you know how to sketch that. Okay, I can ask you questions on that. The other one, 1 over x plus 1, you know how to sketch that, right? I can ask you. Things like this, I'll just say find the linear and quadratic approximations. They won't be sketching. Okay. But these other ones here, right? Sketching this, sketching the tangent line, you have to be able to do that. Okay. And then this one over here. Okay, sketching the function, sketching the tangent line, you need to know how to do that. Yeah. Any questions for the homework part? Okay. So tomorrow we're going to go over error estimation with differentials. Please go over the differences between exact error, relative error, and percentage error. You might have heard that before in physics with your experiments, but if you don't know those, please make a note of that for tomorrow. So exact error, relative error, and percentage error. Okay, we need that for tomorrow. Okay. Any questions about what we did today? Yeah.
The tangent line, it's those lines to the
Yes. Yeah, the points at which the tangent line touches, that's always given. Yeah. Yeah.
You have a vision of the sketch and show.
Yeah. Yeah, like I said here. So for this one, the 2 root x, I could say find the linear approximation and sketch, to show that it's close. So then this 2 root x, you would sketch that. And then this line over here, this one here, then you would sketch that as well and show, the approximation. Or I could say sketch the interval. You'd have to put your round brackets for the intervals there. Yeah. So sketching exponentials, logarithms, trig functions, all of those things you need to know how to sketch. Yeah. Polynomials, all the stuff we covered before. Okay. Anything else? Okay. So tomorrow we'll do the differentials.